Let's try problem 13.16. What is the gas pressure inside the box shown in the figure? Okay, so this problem is pretty straightforward. We just want to know the pressure of the gas inside this box. And so there's a couple things we need to know. First, we need to know the density of mercury, because we're told that this tube is filled with mercury. And so if you look up in the table, we can find that density of mercury, call it rho sub m, is equal to 13,600 kilograms per meter cubed. So that's the density of mercury. And so by looking at this tube, we can see that this end is open to the atmosphere. And so that means that the pressure at the very top of this tube over here, pressure on the mercury, has to be 1 atm. And so another conversion for this problem that we need to know is 1 atmosphere is equal to 101.3 kilopascals, or 101.3 times 10 to the third pascals. Right, I did a unit conversion, so this kilo just means 10 to the third. And so I just made it 100, instead of 101.3 kilopascals, we just have 101.3 times 10 to the third pascals. This will just make our calculations a little more straightforward and let us cancel units. Because you remember the pascal is a Newton per meter squared. Alright, but anyway, so from this picture over here, we know that the mercury at the very top is at 1 atmosphere. And so if you remember our horizontal line rule, that also means that the mercury directly across from it on a horizontal line also has to be at 1 atm. Sorry, that was my phone. And so knowing this pressure right here means that it has to be balanced, right? Because it's essentially an equilibrium. So all the stuff above this portion of the mercury right here has to be providing 1 atm. So the things that are providing pressure above, so we have the pressure from the box, which is what we're trying to calculate, right? Pressure from inside the box, plus this mercury that's sitting on top of it. And if you remember the equation to calculate the pressure with depth, it's just rho, which is density, times the gravity, times the distance above. We'll call it h. So looking at this picture, we know that from this point up here all the way down here is 16 centimeters. And so from up here, just to the middle right here, that's just going to be 16 minus 6, or 10 centimeters. So we know that this distance from here to here is 10 centimeters, right? 16 minus 6. So we're going to use that in a second. But we know, so the pressure of the box plus rho gh has to be equal to 1 atmosphere, right? So let's call it atmospheric pressure. P atmosphere. Right? Just again, so that, because we're looking for the pressure right here, and the things that are going to cause the pressure right here are the mercury that's sitting on top of it and the pressure from the box. And how we know that's at 1 atm is we're using the horizontal line rule. And we know that if we draw a horizontal line and look over here, we know that this mercury right here is at 1 atm. So this mercury over here must be at 1 atm. And so let's go ahead and solve for the pressure of the box. So the pressure of the box is going to be equal to the atmospheric pressure, which is just 1 atmosphere, minus rho g h. Alright, so now we know the atmospheric pressure, so let's just go ahead and fill in. And just to keep our units correct, we'll fill in units of pascals. So this is equal to 101.3 times 10 to the third pascals minus the density, and so that's going to be, right, that's going to be density of mercury, which we looked up in the table, so minus 13,600 kilogram over meter cubed, times gravity, which is just going to be 9.8, meters per second squared, and then times height, and we're told that's 10 centimeters. So let's keep all the units the same. Let's do 0.1 meters. Just to make sure we have our units correct. So let's see. We're going to have a meter on the bottom. We're going to have kilogram. Well, actually, let's just do this. So this is going to be equal to. So when you plug this into your calculator right here, this whole thing, and we'll worry about units in a second. This comes out to 88,000, sorry. And this has the units of pascals. So this whole thing comes out to, let's just make sure our units are correct. So if we're doing unit canceling, so we have kilograms on the top, times meters squared on the top, right? We got a meter here and a meter here, over second squared times meter cubed. And so this is going to equal our meters. We're left with 1 meter on the bottom, kilograms second squared times meters. And if you remember, the Newton is just kilogram meter per second squared. And then this is over a meter squared. And so we're going to left, a meter is going to cancel out. And we're just left with, that should be kilograms, kilograms over second squared meters. Okay, so our units check out. And that's a Pascal. It can also be written as newtons per meter squared. But anyway, here's our answer, 88,000 pascals. And that's problem 13.16.